All right, let's start our last week of notes for this school year. We're still going to be in 11.5 doing some things with induction because there's another type of induction problem. There's honestly several, but I want to sort of break it up so that it wasn't too overwhelming in one big chunk. So you'll see we're still in 11.5 here. Please make sure you've updated your planner and everything else with that homework, and then here's the presentation that will be due by Friday. If you haven't already, please review the plan for the final exams that I posted yesterday, and please let me know if you have any comments or concerns about that plan going forward. I want to make sure that everyone's on the same page. We obviously are still a couple weeks out on that, but let me know as soon as you can if you have concerns. So let's get started on our last week of notes. So as a reminder, induction goes through 3 basic steps. The first one is the base case. And this is where we prove that something's true for n equals 1, for that first natural number. The second idea is that we're trying to prove true for consecutive numbers. So if we know it's true for n equals some k, then it'll be true. We need to prove that it's true for the next consecutive number, k plus 1. And then the last step, which is that algebraic proof of k plus 1. So we did a lot with series last week. This week we're going to look at induction proof using divisibility. So here we have show that 5 to the n minus 1 is divisible by 4 for all natural numbers of n. So feels maybe a little weird to prove with divisibility. Just remember that our definition of divisibility just means if something's divisible by 4 or any other number, this just means that one side can be written as 4 times a number, where, and again with divisibility, x is an integer, right? That it's evenly dividing like that. So we're going to do the same thing that we did previously. We're going to start with n equals 1. So I'm going to plug in n equals 1 here, and the first step is just arithmetic. 5 to the first, 5 minus 1 is 4, which is divisible by 4, right? This is 4 times 1. It's true for n equals 1. So with divisibility, it's again just plugging things in. Now, I'm not going to write out the whole term, this second statement, but absolutely you can. And the main thing with that second statement is it gives us the statement we want. So we want to show that 5 to the k plus 1 minus 1, right? This is our n equals k plus 1, is equal to some 4 times x. That's what we want. Now, let's look at our proof. I'm going to erase, obviously you have plenty of space to keep going with your notes. So just as before, we're going to start with our n equals k. So in this case, we have 5 to the k minus 1 is equal, and we know that it's already equal to some 4x. This might get a little confusing, but these are just different x's. Right, we know that this is true for n equals k. Now, since I want a k plus 1, you're going to be using some sort of creative problem solving skills for these different problems. So I'm going to show you 2 different types. Here we're like, oh man, we've got 5 to the k. We want 5 to the k plus 1. What can we do? I'm going to multiply everything by 5. And at least that gives me one of the terms I want. So now we have 5 to the k plus 1, excellent, minus 5, not as great, equals 4 times 5x, right? This still is a multiple of 4, right? It's divisible by 4 still, so this is all right. It's just a bigger multiple of 4. Now here, we want 5k plus 1, great, we've got it, but we want this to be minus 1, not minus 5. Well, since that's what we want, we can just make that happen. I'm going to add 4 here, because then I end up with minus 1 for my constant term, which is, again, what I want. This is why the want statement is so helpful. But we're following our algebraic order of golden rule, so we have to add 4 to both sides. and we end up with 4 times 5x plus 4. And remember, we wanted to show that this is a multiple of 4. Oh look, 4, 4, you can factor it out, and you end up with this is now plus 1, and we still have a multiple of 4 here. And we have 5 to the k plus 1 minus 1 on this side is equal to a multiple of 4. And again, remember, we know that x is an integer, so we don't have to worry that this is like 2/3 or something like that. So we're done. We can just put our little box or QED right there. So divisibility is a little bit different, but we're still doing the same idea of starting with the n equals k term and doing some manipulation to it. Let's look at another example that's a little bit trickier to just multiply and adding, but I'll show you another strategy. So here, I'm just going to jump straight to the proof. We're going to again start, if you're interested in the first 2 steps, they're in the guided notes. I'm going to jump straight to the proof using n equals k. So we know that n equals k is divisible by 3, so it's some 3x. Now here's where it's really important to think about what we want. And I'm going to put it in the side column here because I don't want to erase it. So we want where n is equal to k plus 1. So when we plug that in, so obviously compared to the last one, this is a much bigger jump to get to from here. So that's why the nice thing about having this want space is I'm going to do a little bit of manipulation to that here to see if that gives me some hints on moving forward. So sometimes manipulating your want, the thing that you want, can give you insight on how to get there from here. So I'm just going to expand all of this over here. So just expanding k plus 1 cubed, we get this whole long thing, and then distributing the 2, we get this. And one thing I noticed right away is that 2 of these terms match. I've got a k cubed and I've got a 2k. And so then I'm going to say, all right, well, that's going to give me k cubed plus 2k, which is what I already have. And then I'm just adding on a bunch more, right? We're adding on this 3k squared plus 3k plus 1 plus 2, which I simplified to plus 3. Hopefully, for thinking about divisibility by 3, oh look, all of these are multiples of 3. Great. So if this is what I want, and this is what I have already, I'm looking over here, I'm just going to add this to both sides. And when I add that to both sides, I end up with that nice big polynomial that I wanted here. So now, we added on the same thing on both sides, so it looks pretty complicated right now. But you'll notice here that we've got our k cubed, whoop, dropped a little link on the 3. And then 3k squared, 3k, I took a 1 from that 3 and then the other 2 down here. And so then we can use the same logic that got us from here, go backwards. This is k plus 1 to the 3rd, plus 2, k plus 1 here, which again, now we have what we want on this side. We just need to show that this is a multiple of 3 because we want to show that it's divisible by 3. And so we can factor a 3 out of all of those. We've got x plus k squared plus k plus 1. And again, we know x is an integer. We know k is a natural number because that's what n is equal to. Oh, it's a nice multiple of 3. Again, we are done. So again, why it's really important to think about what you want first and then figure out what manipulation you have to do in order to get to that point. I'll be available by email or in the comments or on Zoom if you have any questions. Talk to you later. Bye.